last time we finished by reminding ourselves of Oracle machines, and Oracle machines with some bound on the number of steps taken, and we introduced this notation, right? The uppercase, lowercase convention, sort of, that is the use function, the part of the Oracle you really look at. So this U corresponds to the largest Oracle query actually made in the computation on input X by Turing machine E, where E, right? I say Turing machine E, but of course that's it's Oracle Turing machine E, right? So you write the same thing, usually in E, an index for a machine, but now it's a different kind of index because it's an indexing of all Oracle Turing machines. And by now you've thought quite enough about indexing and numbering things that the only thing you need is to be reminded that it's a different indexing. Not much else going on. Then we had the same things where we, instead of A, we wrote sigma, where sigma is a finite sequence of zeros and ones, right? If you think of A as set of natural numbers, then equivalently it's an infinite sequence of zeros and ones, its characteristic function. And so if you only give a finite part, then we consider this as a finite initial segment of the characteristic function of some oracle, and you can just run the oracle computation as long as it doesn't ask anything outside of the domain of the sigma. And in that case, both of these definitions are used, and nothing much happens. So, of course, every function has a graph, but with these Oracle machines, we can give what's known as the Oracle graph. So the Oracle graph of the eth Oracle Turing machine is the set of triples, sigma, x, y, in that order, such that phi of sigma by the eth Turing machine on input x, output y. So this is the Oracle graph of the eth Oracle Turing machine. And one of the first things you notice is that sigmas instead of h, yes. So this means that this is a subset of a countable set. Therefore, it can be looked at as a subset of natural numbers with some coding. What kind of set of natural numbers?
Enumerable, or effectively enumerable?
Computably enumerable, right? This set here is a CE set. For any such triple, you can just start this computation, and if it holds, then you can hold. If it doesn't hold, or you ask an Oracle query outside of this, then you don't put it in there. So this is a nice CE set. Now, the nice thing is, and this is very useful, the nice thing is that this type of CE set completely describes the functional we're dealing with. Right? Because if you give me a functional, then from it I can, well, we just observed, obtain this CE set. But if you give me a CE set like this, if you give me a CE set like this, then you can treat it as a functional by saying, okay, on input x, given some oracle A, I need to try and find out what is the output y. Well, how do you do this? You start enumerating this set, every time you find a triple where the second coordinate is x, you look at the first coordinate sigma, and you ask the oracle queries of your oracle to see if its initial segment corresponds to this sigma. If it does, then you output y. If it doesn't, then you can go back to enumerating g of v until you find the next one. So what that shows is that given a functional and given a CE set like this, it's the same information. Right? These are the same object, just like a function and its graph, and in general are the same object. And computably theoretic, they're pretty close as well. So this is nice because we're not going to do this right away, but at some point we'll be wondering about existence of such functionals. And just building a functional is a complicated kind of thing, but we saw at least one proof in which we build a CE set. And so now if you build a functional, then you know how to do it. If you know how to build a CE set, you go along, you do computable stuff, say investigating whatever you want in a computable way, and every now and then you output one of these triples. Then you generate a CE set of triples, and that CE set of triples corresponds to a functional. And so that way you can build Turing functionals by then enumerating a triple like this is what you would call an axiom for the functional. If sigma is part of the oracle, then on input x you output y. So it gives you an axiom for the functional, and just by enumerating axioms you can generate a functional. Now of course there's a little bit of worry there that if you give two CE sets of axioms, no, I say this wrong. If you give two different enumerations of a CE set of axioms, that you might be describing a different functional. That's certainly possible because if it's just an arbitrary CE set of triples like this, there is no inherent requirement of consistency. Right? There could be two compatible sigma that on the same x give different y. And then what does your oracle do? Well, it depends which one did you find first in the enumeration. I gave a very concrete way of going from a CE set like this to a functional. That certainly works, but it depends on which axiom you see first, how you compute. For a real function, you get what does this say here? Monotone, yes. So we have a CE set which is monotone. Right? If you start with a functional and you get a CE set, then you get something which, if you have sigma xy in GE, then it is the case that for every tau that extends sigma tau xy is also in G. Right? If the part of the characteristic function sigma suffices to compute this output, then having more answers available doesn't change the output at all. In the computation, you're not going to investigate the possible more answers it has. And it's single valued. Also not a very deep insight. Sigma xy and sigma xz, both in GE, then y is z. Right? If it comes from a functional, if a set of triples like this comes from a functional, then this is the functionality requirement. Of course, it's certainly the case that on different oracles it could give different outputs. But as long as the part of the oracle you investigate doesn't change, then for every input you have unique output. We've gone back to pre-calculus now, or college algebra, right? A function is something that for every input has a unique output, and that's the level of observation you're making here. That if the answers to your oracle queries don't change, then the output of the machine doesn't change. Should not be too surprising. Okay, so we call a set 2 to the less than omega. 2 to the less than omega is the set of finite sequences of zeros and ones. So that's the set where the sigmas come from. Such a set is called prefix free if for any two things in this set, not one is a prefix of the other, right? Anything in the set, for anything in the set, all of its prefixes are not in there. Is that a word, prefixes?
Prefaces.
Prefaces? Okay, yeah, so right? For every tau in S, for every sigma, a proper initial segment of tau, sigma is not in S, it's safer, right? And then we can, for a set of axioms, right? Any S of this form is a set of axioms. We say that it's prefix free. Exactly when it won't surprise you once it's finally here. For every x and y, the set of sigma, such that sigma x, y is in S, is prefix free. And this prefix free set of axioms is it's kind of nicer. You don't have a lot of superfluous. That's not how you say that word either, right? Superfluous. Superfluous. You don't have a lot of superfluous axioms in there, right? Here we observe that for any axiom in the set, all extensions are in there as well, and you can economize a little bit by just looking at prefix-free sets. Then it turns out that any Turing functional like the ones we've looked at has a prefix-free oracle graph because you can just straightforwardly define it. You put it in there. If it is in the graph, right? If the computation is done correctly, but moreover, the length of sigma is exactly the use of this function. Right? If you do an oracle computation, then if the computation holds, after the fact you can say, okay, there is this terminal part of the oracle which I didn't need, and the things that are in this FE, the prefix-free oracle graph, are exactly those things where there's nothing too much in the oracle. Well, it's a nice intuition. It's a little false, of course, because you might ask the oracle about 481 without ever asking it about 2. And so in that sense, there might still be too much information in there, but it's just convenient to work with sort of minimal initial segments. And that's what f of e gets us, minimal initial segments. Okay, then some important observations collected in the use principle. And the thing with the use principle is that this, I'm going to be writing this down now, what it is, and talking about it a little bit. Ideally, you're going to be bored by this, because this is, so I like to say, kicking in some open doors, which is not very difficult, right? It's completely straightforward. The only reason you might not think this is completely straightforward is if you haven't gotten sufficiently used to the basic definitions yet. Other than that, if you think about this, there's really nothing going on. But there's nothing going on in such a way that it's sometimes easy to forget in the middle of a proof, and that's why we want to have a name for it, so that we can say, okay, use principle shows that this happens, and then you remember that obvious observations need to be made. If a computation using an oracle terminates, outputs y, then there exists an S, there exists a sigma, an initial segment of A, such that phi of sigma of E of S of X is equal to Y. Right, and you should sit back at this and say, yeah, obviously, if this computation stops, then it stops in some number of steps. Okay, now of course I say again some number of steps again, and we know that when I say a number of steps I'm lying. We're talking about the size of the code of a computation or something like that, and sometimes we even want to say, well, it's not just the size of the code of a computation, it's the size of the code of a computation that somehow in there also encodes a Turing machine, so that these things are sufficiently unique. But whatever you choose for a reasonable way of using this bound S, this is obviously the case. Also, then, if this computation holds, right? If a computation does not hold, you might over time query the whole oracle. But if a computation holds, then it holds in a finitely many computational steps, and in these finitely many computational steps it can only ask finitely many questions of the oracle, therefore there is a maximum question you ask of the oracle. And therefore there is an initial segment of the oracle which is sufficient to answer all of these finitely many questions. Right? Nothing happened. Here is another one like that. If we have this conclusion from the previous implication, that in some S number of steps, using just sigma, you converge, then, amazingly enough, any more number of steps and any additional information results in the same computation. Right? If you already hold in S steps, then you certainly also already hold in T steps, where T is bigger than S. If the only part of the oracle that you need in your computation is sigma, then any extension of sigma will give the same answers to the questions you actually ask, and so it's not going to influence it. Notice in particular, right, we start, if we take both of these computations, we start with an A, an initial segment of it suffices, but now for all also incompatible with the A extensions of the finite part of the oracle, the computation happens in the same way. Like I said, nothing happens. In the same way, like that observation, now having made that and thought it through sufficiently, if such an oracle computation holds and gives output y, then for any actual oracle, right, sigma isn't really an oracle, sigma is the initial segment of an oracle, but then for any actual oracle that extends sigma, it computes in that same way, for exactly the same reason. Right, like I said, I think obviously nothing happened in the use lemma, use principle. There are kind of good observations to make about things being reasonable. Now, and I'm not going to do this, but I'm going to observe something, and that is that, okay, so we defined Turing machines, we defined oracle Turing machines, and these definitions are really close to each other, right? Nicely related. And then we ignored oracle Turing machines up to this point, and we just showed some basic theorems about Turing machines. Recursion theorem, S&M theorem, enumeration theorem, well, we already used it here with the indices. The existence of a universal Turing machine, of course. If you look at the proofs of all of these things, they depended on some mostly straightforward constructions of Turing machines. Right? That's what happened. We took one Turing machine and then we changed it into another Turing machine that encoded part of the input, and as its instructions first put this on the input tape and then start the computation of the original Turing machine. Right? That was the S&M theorem proof. This kind of instructions, it didn't matter whether the machine you started with was a Turing machine or an oracle Turing machine. Right? There's no change whatsoever. Therefore, all of these theorems, recursion theorem, S&M theorem, enumeration theorem, and I'm sure if you go back a bunch more of these theorems, their proofs go through without change in the context of oracle machines. So oracle machines also have an S&M theorem and a recursion theorem and things like that, which is kind of useful. But more important is even the principle. Right? This is the principle called relativization. That if you can do things to Turing machines that aren't too crazy, you can also do them to oracle Turing machines, because they're sufficiently closely related. Okay. So then, having made that observation, I'll make the observation a couple more times in the next theorem. But the next theorem is about this kind of basic construction. This is. Oh, maybe I should first make some definitions. My notes suggest it's better to first define the jump than to prove a theorem about it, which is hard to argue with. This was the halting problem set. This is the relativized halting problem set. And WE super A, of course, means that this is the domain of the eth oracle Turing machine using oracle A. Right? So this is the same set as E such that phi E A E hold. So a very nice uniform definition, and this clearly is reasonably called the halting problem relative to A. We use this enough to want to have a better notation for it. We call it A prime, which is the jump of A. Okay, just because we can. A to the 0 is A to the n plus 1 is A to the n jump. So as soon as you make this definition and you notice that it's a nice uniform definition, it doesn't depend on A really. The resulting set depends on A, but this definition doesn't. You can define this sequence of jumps and get lots of nice things out of it. Okay, so that's the jump, and then we can define or prove the jump theorem. And of course, the halting problem, we've already seen. Well, first of all, the halting problem is, I think, a nice, fairly natural kind of problem to consider, meaningful as well. This is just the same problem relative to A, but what we got before was in this collection of Turing degrees, we had the minimal degree, the computable sets, and then you jump, and we had here the halting problem, and there's a bunch of things in between. And so we have just now made a definition which is going to lead to a similar picture like this, where now we start with A, and we have A jump, and we want to see that we get the same picture like this, and a fair number of questions then later are about how similar these things really are. Okay. Jump theorem. Everybody happy with it so far? Number one. The jump of A is computably enumerable and above A. So first of all, computably enumerable and above. Computably enumerable in A just means that you're equal to one of these WEAs, right? The domain of one of the Turing machines. You can use the same definition. Now again, and again I'm not going to prove this, this was the definition without the A, right? WE being the domain of phi of E was our definition of computably enumerable set. Now I can do computably enumerable in A, and one of the first things we proved about computably enumerable sets is that yes, there's this one thing which is the definition, this is it, but then we have a bunch of equivalent statements, like being sigma 1, like being empty, or the range of a total computable function, like being finite, or the range of an injective computable total function, and all of these same proofs, again, if you look at them, they depended on sort of the notion of Turing machine in general, that if you have this sort of computation, then you can modify it into that sort of computation. And all of these modifications go through in exactly the same way if the computations happen to be orbital computations. One of the things you'll notice, and sometimes you'll observe this and sometimes you'll forget about this, right? A machine like this being the domain, and then finding from it a machine that enumerates it, was take this machine and come up with a different index, which is the machine of an enumerating function. From the index for this to that index that enumerates the function was a nice uniform operation. And so sometimes it's useful to observe that this uniform operation doesn't need Oracle queries. So in that context, even though we're thinking about now a-computable things, the function that from this index goes to one of these other indices is just computable, not a-computable. Right? The transformation of the one Turing machine to the other Turing machine is just computable, no Oracle queries necessary, even though both of them to run need the Oracle. So that's computably enumerable in A. Above A just means that A Turing reduces to this A prime. So computably enumerable above in general means computably enumerable with the Oracle, and this thing Turing reduces to the thing that's above. It's not unreasonable. And then you think about this for a while, and again, we know the proof of zero jump, right? Zero is the empty set, which is a nice representative of the set of computable sets, if you're thinking about Turing equivalence. Zero. So now the halting problem with this definition, the halting problem becomes zero jump, the jump of the empty set. And so if you look at the proofs that the jump of the empty set is computably enumerable and not computable, then, well, I guess above doesn't say strictly above. Above just says above. It's probably item 2. That's not what I wrote here. Yes, so above just says you're bigger or equal, and then the proof that this thing, right, this quick diagonalization that showed that zero jump was not a computable set. If you look at this, then again, we say suppose the halting problem was computable, then we can get this other computation from it which allows us to decide something which we should not be able to decide, or I think we just got a straight contradiction out of it. I forgot, yeah. Again, this depended on suppose this kind of machine exists, then this other machine exists which gives a contradiction. Well, now there's oracles around, they make no difference. So the same proof works. Finally, not finally in the theorem, but finally in the really nothing new to observe category, if B is CE in A, if you're computably enumerable in some set A, then you one reduce to a jump, which is the exact analogy. It's not my day with these English pronunciations. Analog, which is the exact analog of every CE set, one reduces to the halting problem. If you look at the proof, again, the proof doesn't depend on the absence of oracles. If A is CE in B and B Turing reduces to C, then A is CE in C. And this is again one of these observations that is either immediately obvious to you, which is good, or you want to think about it for a while, but you should certainly notice that it is a desirable property. And we certainly already observed that if you're computable in something, then you're computable in anything that has more information in it. And so this observation is the same observation now for computably enumerable. If you're computably enumerable in something, then you're also computably enumerable in anything that has more information. I mean, there's a bunch of easy proofs to try here. One is you are the domain of some B-computable Turing machine, so you have an index for an oracle Turing machine, and then you observe that wherever this index asks an oracle question, you can now put in the computation to find the answer to this oracle question using the oracle C. All other proofs are similar, that as soon as you have this Turing reduction, then oracle questions to B can be translated into possibly many oracle questions in C. But they can be translated to oracle questions in C. And this is a theorem that keeps on giving. 5. B Turing reduces to A if and only if B prime Turing reduces to A prime. Huh? No, that's not what I meant to write. 1 reduces to A prime. leave this for a moment and observe the last two parts of the theorem now, just because this fifth part, in the proof I would want to write something down, and so I'll leave that till the end. If B is Turing equivalent to A, then B jump is 1 equivalent to A jump, and this now of course follows immediately from part 5, where it says if there's a reduction one way, then it becomes a 1 reduction on the jumps. Here you have reductions both ways, so you get 1 reductions on the jump in both ways. Nothing happens. The last item, if A is CE in B, this happens if and only if A is CE in B complement, and this now is obvious from item 4, right? In some of our reductions, a set and its complement are of different complexity, maybe. Right, a cofinite set and its complement are hardly 1 equivalent. But for Turing reductions, a set and its complement are the same in complexity, so this is kind of obvious too. So that just leaves the proof of item 5, or is there any other item I should first say something more about before we do 5? Is everybody happy with everything but 5? Maybe even 5, but then you'll have to sit through the proof anyway. Okay, 5 then. Left to right. Suppose B Turing reduces to A, then we have to obtain that B jump 1 reduces to A jump. And with all the other parts, there's of course one obvious strategy for this, and that is item number 3 in its conclusion has that something 1 reduces to a jump. So if we can show that B is B jump is CE in A, then we get that B jump 1 reduces to A jump. Right? Anything which is CE in some set reduces to its jump. 1 reduces to each jump. But this implication is also obvious. And the only reason I'm writing it down is not because there's something complicated going on, but because there is enough going on that it's hard to remember the different items if they're not in front of you on the board. So this implication is just a direct application of item 3. This implication so you wonder for a moment, and then the first question you could ask, well, I mean, is it true at all? The answer is yes. But how can you, what is a simple check to check whether it's true? Right, this oracle stuff is new, it takes a moment to get used to it, but you know something about no oracle. No oracle, the empty set. Right? If B reduces to the empty set means B is computable, then B jump is computably enumerable. The jump of a computable set is certainly equivalent to the holding problem. Right? If you're wondering, the holding problem relative to this oracle, but any computation done with this oracle could be replaced by just a computational procedure for deciding membership in the oracle, then you just get the holding problem out of it. And And the other way, any computation that goes without an oracle could be an oracle computation. You just don't ask any oracle questions. So that shows that the jump of any computable set is equivalent to the holding problem. I guess I just proved item 6 here for computable sets. But it's good to do because it shows that there's an easy direct proof. Anyway, this is the same way. But you prove it using the other items by observing that, well, A prime is computably enumerable in A, therefore B prime is computably enumerable in B. If something is computably enumerable in B, if something is computably enumerable in B, and you have something which is bigger, then you're still computably enumerable in that bigger thing. Now the letters here are a little bit unfortunate, because in this item we now want A to be B jump, and what do we want? A is B jump, and B is C. A is B jump, B is B, and C is A. I'm pretty sure I got it right. Right? For the application of this first implication over there. Okay, that leaves the other implication. Like I said, we're doing a lot of work, but not really achieving that much. Or it seems like we're not really achieving that much, which is why this is a little bit maybe not the most inspiring lecture. But these are all observations that you need to make. You need to sit back and think about them a little bit, and they're all very important observations. So they need to be made, even though it's a little bit. I find it a little exhausting to go through this one easy part of a theorem after another one. You want to do something interesting and challenging at some point as well, but that'll be coming soon enough. And then suddenly you will also see use of these observations all the time, so that needs to be made. B jump 1 reduces to A jump implies B and B complement are computably enumerable in A. And now I'm not even seeing the opposite observations to make. The next one is at least very easy and it's nice to observe again, because if we have a set and its complement computably enumerable, then it's computable. If you again observe this proof, then the presence or lack of oracles has no influence. Therefore, this it was called complementation theorem or something like that. The complementation theorem with an oracle also works. So this says that now B is computable in A. Which is exactly B Turing reduces to A.